Hi, everybody. I'm Mark, and this is, well, self-introduce.
And I'm Rob.
And this is, if you give a mouse a microchip, it will execute a payload and cheat at your high-stakes video game tournament. And this is going to be a talk about video games, a little bit of hardware hacking, a little bit of vulnerability research, and a lot of trying it out at home. Can't do that either. All right, so brief history of competitive gaming. 1958, kind of the first video game. Your kind of precursor to Pong or Breakout. 1972 is the first recorded, sponsored video game tournament. It was a game called Space War, built in the 1960s, and that was a 5 or 6 player game, competitive, had to run on gigantic lab computers, and Rolling Stone sponsored a Space War Olympics in 72. The prize for which was a subscription to Rolling Stone, which I assume was worth more back then than it is now. This is a picture from last year at the International, which is a Dota 2 tournament. And the International 2016 had teams from all over the entire world. It had a $20 million prize pool. 19 million of it was crowdfunded by fans of the game buying in-game cosmetics, in-game items. 17,000 people were watching that game at the venue live, and over 5 million people were concurrently watching the finals online for the grand finals. So over 40 years, esports has gotten a little bit bigger. And you can kind of see that there's some money riding on it now. So esports events have some kind of unique security challenges. You've got these massive temporary networks that have been set up in a matter of days, maybe weeks if you're lucky, and they might only be used for 3 or 4 days. And you're setting them up in convention centers or in sports arenas. You've got up to 100 or 200 computers or other gaming systems being plugged into them potentially. And you've got hot seat computers, so you'll have stage computers that are set up, and some teams will play on them, and then they'll get off stage, the next set of teams will play on them, and you're going to have all these different people using these machines over the course of the day or the weekend. These computers generally require internet connectivity because pretty much every popular game nowadays has to phone home, so that they're making sure you're not playing on your own private servers or doing anything illegal. And most of these tournaments require you to support player-owned peripherals. Everyone brings their own mouse, everyone brings their keyboard, they're familiar with their devices, they like how they work, or oftentimes they have an obligation to use their sponsor-branded devices as well. Computers at these events typically close a lot of kind of obvious attack vectors. You have internet access restricted, so you can't go to csgocheats.com and download some EXEs, right? Player accounts don't have admin. That's kind of a gimme. Drivers and configs are often pre-installed. A lot of the times you'll have hot swappable SSDs, and every player has a storage device associated with them. So when they plug it into a computer, all of their drivers and setup and everything's all good to go. USB mass storage is disabled, so you can't run your executables off of a thumb drive you sneak in there. And extra USB ports are disabled, often in the BIOS, and sometimes even by dumping some epoxy in there. But again, these players are able to plug their own mouse and keyboard into the computer. So I decided to hack with a mouse. Why? I found a mouse with what I considered to be an overpowered microcontroller. And then I found out more recently that a whole bunch of different mice from a wide variety of manufacturers are using the same family of microcontrollers that has a whole, bunch of extra capabilities that they're not really needing. And anecdotally, I think there's not really enough scrutiny over devices at these esports tournaments, just from what I've observed. Oh, we're missing an image. All right. So I have a gaming mouse with a STMicro STMF32F103CB microcontroller. It's an ARM Cortex M3 processor. It supports their ST-Link programming interface, just to be able to reprogram it easily. It has 128K of flash memory. That's a lot of space, and I'm hoping that there's some space in there for me to add some additional code. It's got lots of buttons. It's got RGB LEDs. Make the kids buy it. So the goal here is to connect to the microcontroller that's built into this mouse, insert some code that acts as a USB keyboard, and when you plug the mouse in, sends a whole bunch of keystrokes to create and then execute a payload on the target computer, unplug itself, and run the original mouse code. And like the point here is, I show up to this esports tournament, I got my mouse and my keyboard. If I plug the mouse in and it does, whatever, and then doesn't work after that, well, now I don't have a mouse. And if I show up there and I plug a mouse in and I look around real sneakily, and then I unplug that mouse and I throw it away and I plug another mouse in, also kind of obvious. So we want to be able to hide our, code injection in the mouse and still be able to use the mouse afterwards so it's, less obvious. So record scratch, isn't that just a rubber ducky and a mouse? Yes, it is. One of the takeaways of this presentation is that all USB devices have microcontrollers in them, and whether it's like an 8 kilobyte PIC microcontroller or a 1 megabyte, ARM super overpowered microcontroller, any USB device can, someone can open it up, attach to that microcontroller, and really replace the code that's on it with anything they want. So these are the hardware tools we used if you want to try this at home. There's the ST Micro Discovery Development Board, which is, it has both an onboard ARM processor that you can use to initially test and develop your code, whatever you want to do with it. And it also has some jumpers that you can disconnect that let you program any external ARM devices. So it can be used both for development and for attaching to your target device. And one of the most convenient things about these boards is that they cost like 10 or 15 bucks. So there is a very low barrier to entry to doing this kind of thing. And then you need a mouse, with an ARM Cortex processor or whatever else you're targeting. You need a soldering iron, you need some wires. Software tools, these are all free. ST Micro made the processor we were looking at, so we just basically used their whole suite of free utilities. And then, we got into ObjDump at the end because we needed to be able to look inside the binaries, and we didn't have the money for IDA.
Sponsor us.
All right, so we open this mouse up, and we see a microcontroller. It's pretty small. You've got a mouse wheel there for size. We need to talk to this microcontroller somehow. So we're going to go to the documentation. We're going to find this eye chart that you see on the right, and it's got, a whole bunch of teeny tiny text on it, and you look through it with a magnifying glass, and you find out that for the ST-Link programming interface, you need pin 14 for clock, pin 13 for digital, like data in out, and the ground pin. And then you get really excited, and you've had a couple beers, and you're like, I'm a really good solderer, and I used to do this in college, and I had a microscope back then and really good equipment, and now I have this little thing that doesn't even melt the solder, but you're like, I'll do it anyways. And you get this. Those pins are real screwed up. And this was the first mouse we lost. So then I flipped the board over, and I found solder pads for ground, clock, and data. Which are the exact pins I needed, right? So the takeaway here is if you spend 30 seconds to look at both sides, right, you can avoid nuking a $60, $80 mouse. So we're on to the second piece of hardware, and we've got our wires connected, and we're doing a lot better. This slide is more to help you along if you're following at home. This just describes the pins on the development board that you need to connect to the pins we just soldered from the mouse. So you can look at that if you want to recreate it. This is that discovery board. We've got this ST-Link connection jumper. You pop those two jumpers off, plug your wires into the mouse. This is our required hacking picture where we have wires, exploding all over the place, and some, some exposed circuit boards. Every presentation has to have one of these. Oh, and my highly technical insulating Scotch tape, because I didn't have electrical tape on hand. So we're attached to the mouse. It's plugged into our programming interface. We plug it in, and it's still doing mouse things, because The manufacturer very smartly disabled things like debug and reprogramming when it's plugged in and out in production. So good job. That was awesome. But we have physical access to this thing. We've opened it up. We've read the manual, so we know how to get it into a programmable mode. So this was a little bit trickier because there weren't any convenient pads for this. So using one strand of stranded core wire, applied 3 volts to the boot 0 pin, which there's an arrow pointing towards it, and ended up actually smoking another mouse doing this because we shorted it out to another voltage line on the processor. It's a little tricky. But on the third mouse, we finally connected to the microcontroller, and this is the ST-Link utility. You can see we're getting a bunch of hex information in the memory there, and we're in. If we want to keep the mouse working and we want to add code to it, we probably want to save this original set of firmware that's running on it. If we just pull this off and modify it and screw it up, we're going to have to go buy a 5th mouse, and I'm running out of my mouse budget is drying up. So we're going to extract this original mouse binary. We're going to build an application that registers as a keyboard, dumps a whole bunch of text on the computer, saves it, and then executes that program. And we're going to find empty space in the mouse's binary and insert our application. And we're kind of just hand waving through that whole code dumping software because it would be really boring to explain to you how to just write ARM code. So we're just going to go through the interesting parts of the hack instead.
All right, so once we're connected, we're going to open up Notepad. We're going to type out an encoded PowerShell script, which is going to decompress itself, fork, and execute in the background. And then it's just going to delete itself after forking because we don't want to leave any traces, right? So what the mouse itself is going to do is save that to temp hack.bat, and that's because, generally speaking, as a user, we can usually write to temp or somewhere along those lines. We're going to close Notepad, and then we're going to run that temp hack.bat. I think it really speaks to Mark and I's friendship that when I was writing this hack, overall, so first off, there's this base 64 encoded like PowerShell script, and then even beyond that, I actually wrote a little hexer Python script that would convert it to hex that he just dumped into a char buffer in the code itself and then just, trusted to run that. So kudos for trust. And so this is basically a slide, if you're following along at home, on basically the syntax to use for objdump to essentially adjust things and get it to basically output in the right form. And so what we're really looking for here is a nice big spot of like just tons of zeros to put our code in. And so it looks like we found that.
All right, so this is going to get a little dry for a couple seconds here, but this is kind of the important information you need to know if you want to build an ARM application at an offset in that ARM processor, because they expect to start at the beginning, and that's not going to work for us. So there's this, since we've found a whole bunch of zeros at address 10A00 in that binary, we think, hey, that's probably a good place to put our code. So we need to edit some files to link, and so that the software knows and compiles for that location. In this flash.ld file, there's actually 2 important things that we found. It defines the size of the stack here, and ARM stack is subtractive, so that's both like the starting point and the size. When we were looking at the binary from the mouse, we noticed that it had a very small stack, like A70, and all the software we were building had a stack size of like 5,000, much larger. And when we tried to run our code with that default small stack size from the mouse, it just completely didn't work. We needed way more space. So that's one of the values that we had to modify. The other thing is that, just specifying the flash memory area, instead of starting at address 8 million, it starts at address 8,010,A00. And then over in the system.c file, we're defining the vector table offset for that same starting point, because there's a vector table at the beginning of your ARM program, and that's important. So the ARM boot process. By default, address 8 million contains this vector table that I just mentioned. The very first piece of data stored there is the location of the stack pointer in RAM. Again, it's subtractive, so it's basically like the size and the location all in one. And then at address 4 is the location of the entry point of your program. So that processor gets power, it sets the stack pointer, and then it immediately branches to the address at that offset 04. And then on the right, there's this little gotcha for ARM programming. If you're doing any branch operation, you have to have bit 0 be a 1, or else it'll hard fault on you, and it's just telling the processor some internal execution mode. So how do we execute our code? We'll patch the vector table. To get the mouse to run our application, we need to find the entry point of the code that we built, and fortunately we so we have to do this obj dump again, do it at the memory offset of where we're running our code out of, and then we just look at the beginning of that file and we can see that our code's entry point is 8013625. So we're going to patch the values at 00 and 04 in that binary we extracted from the mouse with these new values. So on the left in this ST-Link utility, we've got that 2 million A70 and the 8 million 141. And then we just updated those two memory locations for our new code. And now we need to add it to the binary. So using your hex editor of choice, navigate to that offset in the code where hopefully all those zeros are, and use the Elite Hacker tool, copy paste, to add all of your code into that binary. So the mouse should now run our application, and it did, but it didn't do anything else. So I plugged it in, I got this whole keyboard dumping thing, I typed out my program, saved it, and executed. I gave myself a whole bunch of high fives, but then it just sits there and it's a dumb brick afterwards. So we need to make it return to the original functionality. And this is where I called my buddy Rob, and he gave me a whole bunch of help here.
So overall, the really cool thing is you can actually turn basically any device into a rubber duck using the process that we just described using nothing but C code. So now the cool thing is to be able to do this kind of stuff and retain the original functionality of whatever device you're using. And so in comes some sneaky assembly usage where we essentially need to save the state of the mouse kind of as it was before. So this is a picture of how the entire memory of the mouse essentially looks like. And so like from the vector table down to the mouse entry and the mouse and the hack main and the hack end and the hack entry, and then below that's a little bit of our own little data that we inserted there. So all of this is basically just going, everything in red is essentially in main at that point. And so the control flow is the vector table is going to kick us off, and it's going to hit the hack entry, which is then going to call into hack main. And then once we're done executing our payload, we're actually just going to fall through to the end of the, just into the last assembly that's there, which then calls into the mouse entry point, which then runs the mouse. Or in your case, if you are doing any other device that you want to use, it would be that instead. So this is just some of the assembly for what's going on in kind of each of these pieces. So this first part is now our new entry point. So when we patch the vector table, this is the first thing we do. So one of the things we need to save is the address of the stack pointer that the bootloader gave to us to start with. And we also need to push any of the registers that the bootloader might have set up for us that the mouse is going to need. So for any of you that have ever written a packer or done any hot patching, this is kind of how you make sure you don't mess up the state of the thing itself. Finally, we're going to load our hack entry into R0 and go ahead and branch. So now after our application's run and we've done everything bad that we want to do, we're going to fall through here to this jump to mouse code. And essentially this is just going to restore everything back the way it was. So essentially putting the stack pointer back, restoring the registers, loading the desired stack size that the mouse originally wanted because we had different stack sizes, and then setting the stack pointer, going ahead and loading back to, back into R0 the entry point of the mouse itself, and then branching to the original mouse code. And then this is a slide that just basically describes the data that kind of follows after that. These are all of our offsets and other things that we put in there. The really cool thing about when you do inline assembly in C is you can actually use labels. They're really helpful, and they save you a lot of time. And then, and at the very end, we put feed beef, which is just some breadcrumbs, because it gets really annoying to find your code over and over again. So this was just to find it very quickly, and it'll save you some time.
So now we thought that we had, everything good and ready to go. We had, this whole control flow where we power on, we execute our code, we restore the processor state to its original, initialized area, we branch back to the mouse code, and we have a mouse. Unfortunately, what actually happened is we plug it in, it runs our code, our USB hardware input device stops, it goes to the mouses, we see the mouse initialization happen, and then it faults somewhere, and my code tries to initialize again, and we were just getting in this infinite reset loop on this mouse where it was initializing and initializing and initializing and initializing. And one of the more difficult things about this, like I mentioned, was that when the mouse code initialized, all of the debugging was disabled. So I didn't have any insight as to what was happening, and it was basically a black box that just kept turning on and turning off and turning on and turning off. So I'm thinking, how can I fix this? I don't have any information. And I'm looking up, how debugging works on ARM. And I'm like, well, debugging requires interrupts. And I can debug my code. Maybe I can make some changes to this binary. Or, maybe I've screwed something up in these interrupt tables by having my code run before the mouse's code is running. So I, did a little bit of research and found out that ARM interrupts use this change processor state command, and there's a CPS-IE to enable interrupts, CPS-ID to disable interrupts, and there's some flags for configurable handlers and all fault handlers. And at this point, I'm thinking, I'm using interrupts, but I'm probably using, different interrupts than the mouse is using because it needs to be able to register all these button clicks and scroll wheels and, the optical sensor at, some crazy high rate, so they're probably using a lot more interrupts than I am. And I'm thinking, maybe it's using some of these enable or disable commands, and since I've overridden these handler flags, it's actually turning off stuff that it needs. So I'm looking through, and I'm looking for these instructions in the object dump output, and I find two instances where this interrupt disable instruction was being called, and I replaced both of those instructions with a no-op, just skip right over it, and I crossed my fingers, and it worked. So that was really cool. So now we're, fully up, we got a working mouse, we're good to go. So I am thinking that I was just disabling some interrupt that it needed, and, now we're good and happy. And now we're going to try to do a demonstration. So I have this mouse right here. It's got some wires coming off of it because, makes it look cooler. And I didn't bother stuffing them all back in, but we're going to go ahead and try this. So plug it in, or you want to talk about this?
Sure. So overall, this is obviously very obvious. If we were doing it for real, we would do some of the rubber duck tricks to hide this, but this is for you so that you can see the fact that it's working, and it's basically writing it out. Some other things, this is a PowerShell script, and you might be thinking, well, you just block PowerShell and boom, you're done. I think that lacks imagination. So, there are other vectors that you might be able to leverage by writing out. Like, for instance, maybe the game's console itself allows you to type into it, and the command itself, has some kind of vulnerability that gets you code execution, or you write out some kind of HTML, and then just, exploit the browser instead. There's a bunch of different vectors that this kind of technique opens up. And as you can see, he's using the mouse. It worked.
So our little cheat demo here, if you're like Rob and you're not really that good at Doom, you can go ahead and give yourself a whole bunch of armor. And, maybe you want a slightly better weapon. Maybe you want unlimited ammo. And maybe you just want the kill 'em all button.
So for a real hack, generally speaking, in an esports tournament, you wouldn't go with stuff quite as obvious as this. You would professional gamers really only need a little bit more of an edge than Mark and I need. So generally speaking, it's some kind of aim helper that takes like a 3-pixel off headshot and gives it to them as a headshot instead. Very subtle things that are hard to find. And just a little kind of FYI in terms of like detecting the fact that you're cheating like this. Using an external cheat, the anti-cheat technology is very much still in the same spot that antivirus is in, and it's mostly just partial file hashing and maybe a little bit more magic. But as long as your cheat isn't a known cheat and you wrote it brand new for that one, you're probably going to be able to get away with it.
So to kind of close this out, we have more like thought challenges than really a conclusion. Can we defend against extra code in this device? You could have, can we defend against exactly what we did? So you could have your application look at the reset vector when it boots, but you could also have your added code rewrite the reset vector after booting. You could hash your entire flash space, but that would make it so that you can't store user modifications like mouse DPI settings or configs that you want people to be able to save. And you could also have that, added code, change the hash value, or even clear the flash that it executes out of because you have capability to clear flash memory inside ARM. You could get into some more hardware-based tamper detection. These ARM chips have some basic tamper stuff, and then you can buy more expensive secure core ARM chips that have more advanced hardening features. But then you get into this cost trade-off. No one wants to buy a $400 super secure mouse. That's just too much money. So if we're not really going to change the mice around or the keyboards or whatever, can we defend against this kind of payload style? You can only allow, we could get some software to only allow normal behavior from peripherals, right? If I plug in a mouse and it dumps out 2,000 characters per minute, that's, probably not what it's supposed to be doing. You could try to get everyone to sign and verify their drivers and flash of all of their devices. That's never going to happen. Whitelisting executables could get you pretty far, right? If you only allowed the game executable to run on these tournament computers, or if you whitelist executables in your office environment, then people can't come in and hide whatever software they want inside the PowerShell. You could force everyone to use USB to PS2 adapters. That's probably not going to work too well. People like their sub 1 millisecond response rates for their mice and keyboards. And you can provide trusted hardware, right? I mean, if you let people walk in with whatever USB device they have, you really have no guarantee what's running on that. So you might just have to keep a whole stockpile of mice and keyboards for every sponsor and brand and manufacturer and whatever, and just run from there. So we have source code up on a Bitbucket, and then these are all the references we use to get through this whole, process from start to finish. ARM application notes, all the ST-Link utilities, and if there's any questions, I guess we'll be up here.
People were taking pictures. Huh? People were taking pictures of it. Oh yeah.